Hi everyone, Mr. Lee here. In this video, we're going to do a deep dive onto horizontally launched objects. Now, what this means is we are trying to find out all the information that we can from an object that is launched horizontally. We're not necessarily trying to find a specific answer, but we are just trying to unravel all the physics that goes behind horizontally launched objects. So, in this scenario here, we have a ball that is launched horizontally with a velocity of 5 meters per second, and it's released from a height of 10 meters. Okay, so the very first thing that I did is I sketched out the scenario, and trust me when I say that sketching out the scenario, it really does help because it helps organize your thoughts, and visually you can see what's going on, and I think it's pretty effective. Okay, so the very first thing that I want to do is I want to create a variable table. So the first one that we're going to do will be in the x-axis. Okay, so this is all of the variables that is affecting this ball along the x-axis. So we have the initial position, we have the final position, we have the initial velocity, we have the final velocity, we have the acceleration, and we have the time. Now I'm going to add a couple of things next to these variables to help me organize my thoughts even more. So next to this VO, I'm going to add a subscript x. Okay, so this tells me that this is the initial x velocity. So next to this one, I'm going to add a little x. This is my final x velocity. Next to this one, do a little subscript x. This is the x acceleration. Now, the reason why I do this is, one, you can't add the values for your x-axis, such as the value for the x velocity, with values from your y-axis, such as the y velocity or the y acceleration. Okay. Number two, you've noticed that time does not have a x-axis or a x subscript next to it, and that's because time doesn't care. Time doesn't care about the axes at all. Remember, time represents change. All right. Now I'm going to fill in this table here so that we can begin to unravel the mysteries of the horizontally launched projectiles. First off, the initial x position. So we see here that this object is at a height above the ground, but we only care about this horizontal motion. So according to the horizontal motion, right here is the starting point. Along this, I'm going to do a dotted line along this horizontal axis right there. So right there, we can call this our initial x position. And because it didn't give us the numerical value, we're just going to call it 0. That's where we're going to start to measure. All right, x final. X final is how far away this object landed. So if this is the x-axis, and we know that the object started here at x0 is 0 meters, and right here, where it lands along this x-axis, right there, okay, where it lands is your final position. Sometimes you might see this as the total distance or the range of the object, but I'm going to call it the final x position, and we don't know that yet, okay? We don't know that yet. Our initial x velocity, the problem gives us the initial x velocity, and that is 5 meters per second, okay? Now, this is one of those highlight moments. So I'm going to highlight this final x and this acceleration, the x-axis. Unless told otherwise, when you launch an object horizontally, there is none horizontal acceleration. 0. It's always going to be 0. It does not speed up in the horizontal direction because nothing is pushing it sideways while it is in mid-flight. Very important. So that tells us that the horizontal acceleration is 0 meters per second squared. All right. Now remember, the definition of acceleration is speed up, slow down, or changing of direction. And if there is none of those, because that's what 0 means, then that must mean that your initial velocity and your final velocity is the same. Okay? And we don't know the time that it took. All right, so that's my x table. I'm going to do the y table next. Now, see what I do. Instead of writing XO, I'm going to write y initial. Instead of writing XF, I'm going to write y final. So that tells us my initial y position. This tells me my final y position, VOY, for my initial y velocity, VFY, for my final y velocity, A sub y for my y acceleration, and time. And remember, time does not care about the axis at all. Okay, so let's figure out the initial y position. How high off the ground did it start? And the problem gave us that it started off 10 meters above the ground. Okay, we know this object will hit the floor. So basically what this object is doing, if we are to look at it from a side profile, I'm going to do this in blue, it's basically falling to the floor like so. Okay, along that blue dotted axis. So it's going from this height and it's going to hit the floor. And that is what we call 0 meters, because that's the floor. Now, of course, there's going to be some horizontal motion, and with the horizontal motion and the vertical motion, we get this arc. Okay, but if we are just looking at the y-axis, basically it's just going from this high point to the floor. All right, I'm going to bring out my highlighter because this is important. Okay, our initial y velocity, because it's not launched at an angle, but just horizontally, at the peak, the y velocity will always be 0 meters per second. And that is one of those memorized ones. Please, please, please don't forget that. We don't know how fast it'll land on the floor, but the acceleration, we do know that this object will accelerate. And it's going to accelerate at negative 9.8 meters per second squared, because that's the acceleration due to gravity. And we don't know how long it'll take in the air. Okay? All right, so here we have our tables, and the rest is a lot like the other projectile motion problems that we've done before, the kinematic stuff. Okay, so the very first thing that I want you to do is always try to find the given time. All right, I would say about 90% of the time, you want to find time first. I'm going to bump that up to about 99. And in order to find the time, and this is why I'm going to bump it down a little bit, down to 90%, we are going to find the time along the y-axis, because the object hitting the floor is what's stopping the motion of this projectile. Okay, once it hits the floor, like, we know how far it went, we know how long it took, but it has to hit the floor, so it has to go along the y-axis. Right? So I have my equations here, and I want to find the time. Same strategies. Right? I'm going to take a look at the equation, and I'm going to ask myself, do I have this variable? And if I do, I put a check mark and I move on. So, do I have the y final velocity? I don't. Okay, so if I don't have that, I can't use it. All right, next, do I have the final y position? I do. Do I have the initial y position? I do. Do I have the initial y velocity? I do. Do I have the time? I don't, but I'm looking for it. Do I have the acceleration along the y-axis? I do. Do I have the time? I don't have the time, but I'm looking for it. Check. So I found the equation that I'm going to use. Right? So I'm going to do this in blue, just so that it's a little bit more clear for us. But I'm going to find the time, and the very first thing that you always want to do is you want to write out the equation. So we have x of f is equal to xo plus v initial times the time plus 1/2 at squared. Right? Now, once you get the hang of it, you can leave it in this format and be like, okay, I'm using the y variables, but when we start off, let's change all of this so that it reflects what we have here in our table. So instead of writing x of f, I'm going to write y sub f is equal to y initial plus v initial y times the time plus 1/2 a times the time squared. Step 2, I'm going to put in the zeros where they belong. Our final y position is a 0. Our initial y velocity is a 0. And what that helps us do is that cancels that out, because anything times 0 gives us 0. So our cleaned up equation looks like this. 0 is equal to y initial plus 1/2 times the y acceleration times the time squared. Okay, and we want to find the time, so I want to rearrange this equation so we have isolated the time variable. So I'm going to subtract y initial from both sides. Okay, and y initial minus y initial, that cancels out. So we get negative y initial is equal to 1/2 a sub y t squared. I have a 1/2 here. I want to get rid of it, so I'm going to multiply both sides by 2. Okay, because we have 2 in the numerator, 2 in the denominator. And so what happens there is that these cancel out. All right, and that leaves us with negative 2y initial is equal to a sub y t squared. All right, I want to divide both sides by a sub y. We have a sub y in the numerator, a sub y in the denominator. Cancel that out. That leaves us with negative 2y initial divided by a sub y is equal to t squared. And the very last thing we want to do is square root both sides. Because when we do that, the square root cancels out and the square cancels out, leaving us with time is equal to the square root of negative 2y initial divided by a sub y. All right, so here we have this equation. I'm going to move the camera or the screen up a bit so we can see this a little bit easier. Okay, now I'm going to plug in my my numbers. So we have time is equal to the square root of negative 2. The initial height was 10 meters divided by negative 9.8. All right, so if I were to plug that into the calculator, let's see, where's my calculator? There we go. Plug that into the calculator. We get, why is it so big? All right, we get negative 2 times 10, okay, divided by negative 9.8. Okay, and then we take the square root of that, and we get 1.43 seconds. 1.43 seconds. Make sure I got that correct. All right. So I'm going to write that time value up here. Okay. I'm going to write that in black because that is a universal one. 1.43 seconds. And remember, the time for the x-axis and the y-axis, they're the same. Okay. So we found out how long it'll take to fall. So at this moment, we can figure out the final y velocity as well. So let's do that. I'm going to take a look at my equation here. Let's move this over here so that we have a little bit more space. If I want to find out the final y velocity, I'm going to see, do I have the final y velocity? No, but that is something that I want to find. Put a check mark there. Do I have the initial y velocity? I do. Do I have the y acceleration? I do. Do I have the time? Well, yes, now I do. All right, so I'm going to start off by writing out my equation. I'm going to do this in, actually, oops, let's do this over here. Let's keep all my y stuff over there. So we have Vf is equal to V initial plus acceleration times the time. I'm going to rewrite this so that it's for the y-axis. Okay, it just helps me organize my thoughts. And now I'm going to put in the zeros where they belong. We know that the initial y is 0, and that's the only 0 here. So we have v sub y is equal to a sub y times the time. Okay, arrange it so that it's in the form of the variable we're looking for. Luckily for us, the form is already there. A sub y is negative 9.8, and the time is, what was it, 1.43. Okay, so we know that the final y velocity, now this is not the total, but the final y velocity is, dun, 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 9.8, negative 14.014 meters per second. Now remember that negative, because we're in the y-axis, that means that that negative is, the object is moving in the downwards direction. Okay, so let's write that in right here. Negative 14.014 meters per second. All right, so we have our entire y table filled out. Now remember, we're not necessarily looking for anything. We're just doing a deep dive in this problem so that we can find out all the necessary information just in case this problem pops up and something very specific is asked. Now let's do the x table. Okay, notice that the only thing that we're missing is how far out it goes. So let's figure that out. Okay, how far out does this object go? I'm going to do this in, let's do this in green. So we want to know the final x position. So I'm going to go to my table. This equation doesn't even have final x position, so I can't use that. Okay, final x position, check. Initial x position, check. Initial x velocity, check. Time, check. Acceleration in the x-axis, check. Time in the time overall, yes, check. All right, so we can use the second equation. So I'm going to start off with the equation the way that it is written. Okay, and next what I'm going to do is I'm going to clean it up by rewriting all the variables so that it's in the form of the table. So we have v initial x times the time plus 1/2 a sub x, because we're in the x-axis now, times squared. Okay, we want to now put in the zeros where they belong. Zeros are there, and the acceleration is also 0. Okay, so when you have 0 times 1/2 times time squared, that all cancels out. Let's clean this up in the next step. X of f is equal to v initial x times the time, and all of that is 0. We want to know how far out it goes. Okay, so that's the equation. Now we can plug in the numbers. So v initial x is 5, and the time is 1.43. So if we were to plug that into the calculator, we will get, let's see here, 5 times 1.43, that gives us 7.15 meters per second. Now, there's a positive there, and that positive simply means that it's going to the right. Okay, I'm going to write that down there. So we got 7.15 meters, oops, not meters per second, excuse me. That should just be meters, because that's not the velocity. My mistake. Okay, 7.15 meters. All right, so that's how far out it lands. So we know that when this object is launched from a height of 10 meters, it will go out 7.15 meters. Okay, all right. Now we're not done yet, because sometimes it might ask you, with what velocity does the object land? Now we have, if we were to take a look at this object right there, as soon as it hits the ground, remember, the object does not have 0 velocity. But what we can do is we can use the x and the y velocities to figure out the actual velocity of the object. So we did the y velocity in blue. So at that moment, as soon as it touches the ground, this object has a y velocity. Okay, this arrow is going down to show us that the velocity is negative. Vfy is negative 14.014 meters per second, and it also has a horizontal velocity, okay, as a horizontal x velocity, like that. And this horizontal x velocity is 5 meters per second. Let me write that as an F. All right, so we have these two velocity vectors that can describe to us what's happening with this object. So what this tells us is that as soon as it hits the ground, this object is moving forward at 5 meters per second, and it's moving downwards at 14.04 meters per second. Now, that helps us describe the x and the y motions, but it doesn't tell us the overall motion. And for that, we're going to use some fancy Pythagorean theorem stuff. All right, so let's see if I could get this. Yeah, let's get that. Let's copy, and I'm going to go down here, but I have a little bit more space. All right. So we have the problem right there. Okay. Now I'm going to clean this up a little bit. I'm going to make this a little bit bigger. So we know that this object is moving forward. Okay, and that velocity is 5 meters per second, and it's also moving downwards at 14.014 meters per second. So if we were to combine these two velocity vectors, I'm going to do this in black, we get a down and rightward velocity vector. So this is the actual velocity of the object. And in order to do that, okay, in order to find out the actual velocity of the vector, I'm going to show you something really, really cool. All right? I'm going to take this y velocity. Let's see if I could move this. Yeah, let's see if I could do this. I'm going to get this y velocity. Oops. And I'm going to move it to the right. Now bear with me here. I'm going to create something cool. Yeah, look at that. All right, so I move this negative 14.14 velocity over to the right, and I created a very special shape. And this is a special shape here in math, because that is the triangle. Wow. that right there is a right angle, so this makes it a right triangle. Okay, and that is whatever angle that is. So we want to find this final velocity. Now, if this is a right triangle, we have to use a formula called the Pythagorean theorem, okay, which tells us that if we have a squared and we have b squared, we can find c squared. Okay, a squared plus b squared is equal to c squared. So we have 5 squared plus negative 14.014 squared, we get c squared. Okay, so this gives us, I'm going to do everything else in black, or I'll keep up though. That's 14 and negative 14.014, let's see, squared, 14.014 squared gives us 196.39. So 196.39. Okay. And in order to get rid of the square root, I'm going to square root both sides. And our final answer is, well, let's take a look, plus 25. Okay, and then we square root that. And our final velocity is 14.88 meters per second. Okay, so the object is hitting the ground with this velocity vector, so it's going forward and down at 14.88 meters per second. Now, this is the only way we can add x values with y values. Okay, instead of just adding the negative 14 to the 5, only in the world of physics, this is the only way that we can add the x values with the y values. All right, so this tells us a lot, right? This tells us that the object is going 14.88 meters per second, but doesn't tell us the direction. Well, we can say that it's going down and to the right, okay, down and to the right. But if you want to find the actual angle, okay, if we want to find this angle here, we got to use some trigonometry. So we have, according to this angle, this side of the triangle is the opposite. Okay, and according to this angle, this side of the triangle is the adjacent. So what we get is a opposite over adjacent formula. Now, if you remember SOHCAHTOA, I'm going to write this up here. SOHCAHTOA. Okay, we want one of these trig functions that tells us the opposite and the adjacent. So we got to use the tangent function. Okay, so the tangent theta is equal to the opposite over the adjacent. So if I want to find theta, my opposite side is negative 14.014 divided by the adjacent side, which is 5. Okay, and if I take the inverse tangent of this, like so, that tells us the direction of this object, or the angle, and let's see if this calculator can do that. So a couple things that you need to know. You need to be in degree mode and not radian mode on your calculator. So I'm going to go into my scientific calculator. We are in degree mode right there, so we are good. Let's do the inverse tangent of negative, oops, let's erase that. So we have negative 14.014 divided by 5. That should be a negative. Okay, so negative 14.014 divided by 5 gives us negative 2.8028. I'm going to take the inverse tangent of that. Cool. And so that gives us the angle of this object, which was negative 70 degrees. Okay. And so instead of saying down and to the right, if we want to be a little bit more specific, we can say that this is moving 14.88 meters per second at negative 70 degrees. All right, so let's break this down a little bit more. what did we just uncover? We just took a very deep dive on horizontally launched objects. Okay, I highlighted all the very important information that you need to memorize. One, at the peak, the y velocity is 0 meters per second. The acceleration in the x direction is usually 0 meters per second squared if they don't give it to you. And the initial and the final velocities, they're the same because of the definition of acceleration. I also showed you how to break down the table so that we have the x and the y direction. Okay, very important here because remember, you can't just add x values to y values. We have to use a special technique. All right, and with this special technique, I showed you how to combine the x velocity with the y velocity, and this is something that will pop up with a lot of the physics units where we combine the x and the y values. It could be things other than velocity. All right. Also showed you how to find the angle, or this angle right there, of the object. So if we were to ask, or if you were to be asked, with what velocity does this object land on the ground with, we now know that the object lands at the ground with 14.88 meters per second down and to the right at negative 70 degrees. We also know how far out it went. Okay, it went out 7.15 meters. We also know that it took 1.43 seconds in order to reach its destination. All right, so this was a lot. But like I said, this was a very intense, in-depth look at horizontally launched objects. This was Mr. Lee. I will see you next time. Bye-bye.